All right, welcome. Today, we're going to go on a little journey. It's a trip that starts with a whole mess of raw data and ends with those super smart predictions that basically run our digital lives. We're going to break down how machine learning really works, especially on the cloud. So let's get into it.
You ever stop and think about that? How your phone just knows the exact movie you're in the mood for, or the perfect song to listen to next? Well, that's not magic. Not at all. It's machine learning. It's the engine running behind the scenes of pretty much every personalized experience we have now. And today, we're going to pop the hood and see how that engine actually gets built.
Okay, so first things first. Before we can build anything, we have to know where we're building it. And for modern machine learning, that place, it's the cloud. Let's dig into why this shift has been such an absolute game changer.
So what even is machine learning when you strip it all down? Well, it's really just about teaching computers to learn from examples, kind of like we do. Instead of writing out a million lines of code for every single possibility, we just feed the machine a ton of data and let it figure out the patterns for itself. It's the classic difference between giving someone a fish and actually teaching them how to fish.
And this really gets to the why. Back in the day, if you wanted to do this, you had to buy these giant, super expensive servers that you had to manage all by yourself. And if your project got bigger, well, you had to go buy more servers. It was slow, it was painful. The cloud just completely flips that on its head. Now, you only pay for what you actually use. All the updates are managed for you, and you can go from a tiny little experiment to a massive global app, like instantly. That flexibility is what's really unlocked all this innovation.
So every single machine learning model, I don't care how fancy it is, runs on one thing: data. But here's the catch. It can't be just any data. It needs clean, high-quality, refined fuel. You can think of the model like a Formula One engine. You wouldn't just pour crude oil into it and expect it to win a race, right?
And that brings us to what might be the biggest open secret in all of machine learning. Yeah, building the model is the glamorous part, but the part that takes up the most time, and honestly is probably the most important, is just getting the data ready. If you look at standard industry processes like CRISP-DM, it's clear. This is where data scientists spend most of their time. You have to get this part right. So where does all this data actually live in the cloud? A lot of the time, it's in a service like Amazon's S3, which is basically a giant, infinitely scalable hard drive. But see, not all data is the same. You can pick different storage tiers depending on how often you need it. The stuff you need right away, that goes in S3 standard. Data you use less often can go into a cheaper standard IA tier. And data you just need to keep for compliance, maybe for years, you can archive that in a super low-cost Glacier storage. It's all about making sure you're not paying for speed you don't need. So how do we get from that raw data to the high-grade fuel? It's really a three-step pipeline. First, you just collect and store everything. Then comes the cleaning. This is where you fix errors, fill in missing pieces, and get rid of any really weird data points or outliers. And finally, you transform it. This part is often called feature engineering, and it's where you mold the data into the exact shape the algorithm needs to learn from it properly.
All right, our fuel tank is full of clean, premium data. We are ready for the main event: training the model. This is the learning part of machine learning. This is where the algorithm goes from being a blank slate to a smart, digital brain that can actually make predictions.
Now, generally speaking, this training comes in two main flavors. First, you've got supervised learning. This is where your data is all neatly labeled. You already have the right answers. It's kind of like studying for a test with a big stack of flashcards. You've got the question on the front and the answer on the back. You learn the patterns to predict the answers. Then you've got unsupervised learning. Here, there are no labels, no answer key. The whole goal is to just give the algorithm a huge pile of data and say, find the interesting patterns in here, like grouping similar customers together without being told what the groups should even be.
A really common supervised algorithm you'll hear about all the time is something called XGBoost. Now, it doesn't just build one giant, complicated model. What it does is it builds hundreds, sometimes thousands, of really simple little models. Think of each one as an expert giving their opinion. The final answer is decided when all these experts just vote on it. It's this team effort, this ensemble approach, that makes it so incredibly powerful. And on the unsupervised side, you have algorithms like k-means. This is your classic tool for finding clusters. You basically tell it, hey, I think there are probably 5 groups in this data. That's the K. The algorithm then goes and finds the 5 best center points and assigns every single data point to whichever center it's closest to. It's a fantastic way to discover these natural groupings in your data that you probably didn't even know were there. So, we did it. We've trained our model. Our digital brain is, well, it exists. But is it any good?
This brings us to a super important step, evaluation. This is basically the final exam for our model before we can trust it out in the real world.
For a lot of problems, one of the best tools for this is something called the confusion matrix. And I promise, it's way simpler than it sounds. It's just a report card. It shows you exactly where your model's getting things right, and more importantly, where it's getting things wrong. So for a fraud model, it shows us when we correctly spotted fraud. That's a true positive. But it also shows us when we missed it, a false negative. That's a big oops. And then it shows us when we wrongly accused a good transaction of being fraud, a false positive.
Okay, so we've got this grid with 4 numbers in it. Cool. But what does that actually tell us? How do we turn that into something useful? Well, this little box gives us the building blocks for 2 incredibly important ideas.
First up is precision. This one's all about how many of your predictions were actually correct. It answers the question of all the times we cried fraud, how often were we right? If you flag 100 transactions, but only 80 of them are real fraud, your precision is 80%. You need high precision when making a mistake is really costly, like accidentally blocking a good customer's credit card.
The other side of that coin is recall. This is all about how much of the real fraud you managed to catch. So if there were 100 fraudulent transactions out there in total, and your model found 90 of them, your recall is 90%. You need high recall when missing something is the real disaster. And this creates this classic tension. Would you rather annoy 10 good customers just to catch one bad guy, or let one bad guy slip through to keep all 10 of your customers happy? Finding that perfect balance is the real art here.
So, our model passed its exam with flying colors. It's been trained, it's been tested, and we're feeling good about it. Now for the really exciting part, deployment. This is where we take our model out of the lab and actually put it to work, where it can start creating some real-world value.
At the end of the day, deployment is all about building a bridge from the super smart model we've built to the apps that actually need to use its brain. This bridge lets an application send some new data over and get a prediction back instantly. So let's see how that bridge gets built.
So if you've gone and built your very own custom model, the playbook pretty much looks like this. You train it on a cloud platform. Then you deploy it as what's called an endpoint, which is just a fancy name for a secure private web address that only your applications can talk to. Then your app can just send new data to that address, and the model sends its prediction right back. It's a really clean and scalable way to get your model working.
But what if you don't need a totally custom solution? Well, the cloud also gives you a fast lane, pre-trained AI services. These are basically incredibly powerful models that are already built and ready to go for common tasks. You need to understand what's in a photo? There's a service for that. Need to analyze some text? Yep, service for that. Build a chatbot? You guessed it, there's a service for that too. It's like hiring a world-class expert on the spot instead of having to train someone from scratch.
And maybe the most important thing to take away from all this is that this entire journey, it's not a one-time trip. The world is always changing, right? New data comes in, people's behavior changes. This can cause your model's performance to get worse over time. That's why this process has to be a cycle. You have to constantly be monitoring your models, evaluating them, and retraining them with fresh data to keep them sharp.
And that brings us to the end of our journey. We've seen how raw data becomes fuel, how these digital brains get trained, and how we put them to work in the cloud. We've essentially given machines the ability to learn from the past. So the real question for all of us is, what's the most important problem we should teach them to solve next? Thanks for joining me.